Hello everybody, this is our lecture on sampling distributions. That term's a little bit weird, but we'll actually demonstrate what that is in a bit. And this is our first lecture of Unit 2. So just to remind us where we've been already. In Unit 1, we went over various descriptive statistics. Those describe a sample, and we always know specifically what descriptive statistics are because it's like an average. So an average, we know what the average is for the sample. We can calculate it. We can also calculate the standard deviation for the sample. So descriptive statistics just has to do with the sample. And we know those things for sure. And the nice thing is, as we're transitioning to inferential statistics, we're going to be using means and standard deviations a lot. So it's not just using those for descriptive statistics, but those help us think about inferential statistics. And we actually started to do that with our z-scores. So when we started looking at z-scores, we were looking at the difference between a score and the mean, and we were making judgments about how close it was or how far it was from the mean based on the standard deviation, because z-scores converted that difference into standard deviation units. And so we're actually now making judgments about how far things are apart from each other. And we started using the z-table, the normal curve tables, and those told us about probabilities. And so all of these concepts, means, standard deviations, things like the z-scores, are helping us make that transition into inferential statistics. And we started talking about the normal curve probabilities in terms of likely and unlikely events. If it's closer in terms of the z-score, it's closer in terms of standard deviation units, a score from the mean, and then it's not really that different. It's pretty likely to have a score close to the mean. But then we talked about when you have things that are higher z-scores, when you're farther away in terms of standard deviation units from the mean, those are more unlikely. Remember that the normal curve, we have a lot of stuff in the middle, and we have fewer things at the ends. And so we're starting to talk about likely and unlikely events in terms of scores. The score is close to the mean, it has a lower z-score, then it's a pretty likely event. There's lots of people with scores in that area. If you have a score far away from the mean in terms of z-scores and standard deviation units, it's less likely. There's fewer people out there on the ends. So all of these things that we've been talking about is making that transition into inferential statistics. Inferential statistics, just remember, is we're taking our samples data and we're making some sort of conclusions about the population. And remember, we talked about the sample can never perfectly represent the population. And so when we're talking about inferential statistics, we're talking about probabilities. So we find something in our sample, how probable is that going to describe, going to be true for the population? We can't say it's for sure true or for sure not true. We say there's a certain percentage. There's a probability to those types of statements. So all that stuff that we talked about with the z-tables and the z-scores, and we're starting to talk about probabilities under the curve, that's what we're getting at. We're getting at being able to take those probability statements from the normal curve. And as I said in the last lecture during z-scores, those normal curves are stable. Every normal curve, every standard normal curve has those same percentages. And that's stable across time, across normal curves. It just always applies. And that's good because when we're doing research and we're making these probability statements, we want to be fairly specific about our probability statements. We can't change those things, and they don't change. And so those stable probabilities we talked about with the normal curve are going to underlie inferential statistics. And so what we're going to be talking about today is sampling distributions. Sampling distributions can be a little bit theoretical, but what I'm going to do is I'm going to demonstrate it to you. And these sampling distributions really will also underlie inferential statistics. The logic behind them is sort of the underlying logic of inferential statistics about making probability statements from the samples data to make some sort of conclusion about population. Again, those conclusions are couched in probability, but those probabilities are related to the sampling distributions we're going to do today. So let's go ahead and talk about it a little bit, but we're going to demonstrate this. So if you don't get this right away, that's fine, because we're going to actually demonstrate this. So if you want to think about research, it's pretty easy to think about research in this way. We have some sort of population. So we have a population of people. We can just say human beings. Let's be really grandiose. So we want to make some sort of conclusion about human beings. We can't sample all human beings. And so we'll take samples. So we might take a sample. Let's say our sample size is pretty large. Let's say it's 100. So we can think theoretically that, okay, I could do a sample of 100. Some other researcher could take another sample of 100 people from the population. Somebody else will take a sample of 100. And so that's what we call by taking samples of the same size. And so if we just think theoretically, if we take a bunch of samples of 100 people from the population, and then we would run our studies with each of those 100 people. So each of those samples would be of 100 people from the population, and each of those samples are probably pretty independent. There might be a chance that somebody might be in more than one sample, but basically those samples are different. And then we can examine some sort of statistic. Let's say mean. So let's say I want to do research on narcissism. I'm curious about Americans. We'll just say Americans in this case. How narcissistic are Americans? So that's my population. So I can sample 100 Americans and measure their narcissism and get a mean of narcissism for that sample. I can take another sample of 100 people. I can measure their narcissism, and I can get the mean of that sample. So the mean is a statistic, and I'm running different samples with 100 people each, and I can find out the mean, the average for each of those samples. And then what I can do is I can plot that mean into a frequency distribution. So I can plot that mean into a frequency distribution, and that's what we call sampling distribution. So instead of plotting individual people's scores, we're plotting the statistic from each of the samples. So what I'm going to do is I'm going to demonstrate this. That's basically the definition. I think it's much better to demonstrate it. So let's do this. So normally I do this in class, but we're not live, and so I'll have you think about this, but I have some numbers that we can use. So let's say that we're in class, and then I ask you to take out a coin. And I ask everybody in class to flip the coin 10 times. And I want you to count the number of heads. So this is actually a sampling distribution. So each person in class is flipping the coin 10 times. They're counting the number of heads. So the sample size is 10. So each of these, each person is a sample. Each person has 10 coin flips. That's the sample. And let's say that we have a class of 30 people. So I would have 30 samples with 10 coin flips each. So that would be a sampling distribution. And what is the statistic we're looking at? The stat we're looking at is just simply the number of heads. So I'm going to ask you about your number of heads. And it can go from 0 to 10, right? Somebody might get no heads out of 10. Somebody might get 10 out of 10. But there would be a range of 0 to 10. And then what we can do is we can actually take those numbers and we can put it into a frequency distribution. That would be a sampling distribution. Something to think of before we get headed here is what would be the population value for that? So if we have 10 coin flips as our sample size, if we took an infinite number of 10 coin flips, what would be the average number of heads for the population? I hope you're saying 5. If the coin is a fair coin, and there's a 50-50 probability, 50% chance it's going to be heads, 50% chance it's tails. if we flipped a coin 10 times, many times, so we had many samples of 10 coin flips, the population value would be 5 because it would be 50-50, be 50% chance. So the samples might differ. The samples might differ in terms of the number, but if we took all of the infinite number of 10 coin flips, everything in the population, it would be 5. So just keep this stuff in mind as we go further. So just remember that coin flips is one sample. So our n is actually 10. So we've had n before. So the number of scores, for example, when we're calculating the average. So our n here would be 10 coin flips. So what we're going to do is I'm going to show you some random numbers. These random numbers are from 0 to 10. So they're simulating us actually flipping the coins in class. So we're not live in class. I can't do it. I've done it before and it works out the same way. But I'm going to take random numbers. They're from a random number generator. So it's going to simulate what we would actually have in class. And what we're going to do is we're going to look at the mean number of heads. And this is for each sample per 10 coin flips. So what is the average number of heads per sample, per 10 coin flips? And that's going to be a mean for a sampling distribution. We'll talk more about this in a bit. I think it's better when we see the actual numbers. And then I'm going to plot the histogram of the data. And this will show us the shape of the distribution. And then I'm going to show you this thing called standard error. So the standard error, the mean, is a bit of a new concept, but it's not that difficult. Basically, the standard error is related to this. The standard error is simply the standard deviation. We all know what that is. The standard deviation is the average distance from the mean. But in this case, we divide the standard deviation by the square root of the sample size. And so in this case, the sample size is the number of people doing the coin flips. So it's not the coin flips. The coin flips are 10. So we're taking samples of 10, but we're looking at how many samples. So the n here is not 10. The n is how many people are we getting numbers from that did 10 coin flips. So how many samples do we have? It's not how many coin flips, it's how many samples of 10 coin flips we have. And you can see here, this is the sampling error of the mean. I'm sorry, the standard error of the mean, but it's the sampling error too. Basically, it's an estimate. So we're asking ourselves, how good is our estimate? So when we're estimating the mean, how good is that estimate? A bigger standard error means that we're a little bit unsure. We're estimating the mean, but we're not sure. It could be a broad range. If it's narrow, if it's a small standard error, we're saying we can make a pretty good estimate about the mean. We're not going to make a lot of errors. So that's what we're doing here. And when we're talking about inferential statistics, we'll see this. If you don't get this right away, this is fine. But basically, a big thing about inferential statistics is the more information you have, the better your estimates. So remember, in descriptive statistics, they're not estimates. We know what a mean is for a sample. But when we're doing inferential statistics, we're making estimates about the population based on the sample's data. And so what this is basically saying, the standard error, if it's large, we're a bit uncertain. There can be a lot of error in our estimates from the sample to the population. So when we make inferences about the population from the sample, we have to be a bit more iffy. If the standard error is small, again, we have a lot of information. We have more information, we can make a better estimate. We make a better estimate, we can be a little bit more certain about our inferences, our conclusions about the population from our samples data. And we'll get into this a little bit more as we go on, but I do want to get into the example because we have the example coming up. This is the formula for the sample. Here, this is the formula for the population. This is the formula for the sample. It's just saying the same thing. The standard error of the mean is the standard deviation over over the square root of n. So n again is the number of samples. It's not 10, it's the number of people who did 10 coin flips. Okay, so let's go ahead and do the actual thing. So I have some stuff here and I have to go back and forth. So these are randomly generated numbers from 0 to 10. So this is simulating as if we were doing the 10 coin flips in class. So let's say I asked you to do the 10 coin flips in class. This is what I would do if we were live. I would ask the first 10 people. So I'd ask the first 10 people to give me their data. So if we look here, these are randomly generated numbers, but these would look like what we get in class. So person number 1 got 3 heads. Person 2 got 7 heads. Person 3 got 5 heads. Person 4 got 6 heads, and so on. So these are the number of heads out of 10 that the first 10 people got. So I'm going to cut and paste that into SPSS. So again, this is for the first 10 people in class and the number of heads out of 10 coin flips that they got. So we're taking a sampling distribution. The sample size is 10 coin flips. And we're actually taking the first 10 samples. We have 10 people here who did this. And so we have 10 samples also. So let's go ahead and run the statistics. I'm going to run frequency distributions. I thought I didn't reset this. So we want the mean. It's right here. We want the standard error of the mean. We want to get the histogram. We want to see what it looks like. And so we're just going to look at this as we add more samples. Well, let's just do it. And actually, let's look at the numbers. So here we go. So here's our mean. Hopefully you can see it here. It says here the mean is 4.2. So our average number of heads out of 10 coin flips for the first 10 people, the first 10 samples, was 4.2. That's actually not too bad. We're not too far from 5 right away. What's the standard error of the mean? So the standard error of the mean is right there. I hope you can see that. It's the last number right here. I'm going to round up. That's 0.83. So our standard error of the mean is 0.83. And what does our distribution look like? So let's look at the histogram. What does it look like? It looks kind of weird. Basically, we go from 0 to, looks like we have an 8. Yep. So we have a bunch of different numbers from 0 to 8. They're all 1 except we have, just by chance, we have 3 5s. So we might call this a unimodal distribution, but I would definitely not call it normal because we don't have that slope going down. It's just kind of flat except there's one number that has 3 versus 1. So I'm just going to call it flat with 1 mode. And I'm going to put in parentheses, not normal. It's definitely not a normal distribution. Oops. Okay, let's take 10 more people. So I've randomly generated 10 more numbers. So let's say that this is what I would do in class. I would take the next 10 people and ask them how many heads they got out of 10 coin flips. And now we have 20 samples. So when I say n here, I'm talking about the number of samples. We're actually going to have 20 samples. We have 20 people who flipped the coin 10 times. And so here's the numbers that were randomly generated, sort of simulating what we would get in class. And I'm going to put that over into SPSS. I'm going to close this. And here we go. So now we have 20 people, so we have 20 samples of 10 coin flips. Again, that's a sampling distribution. Sampling distribution, we have 20 samples, with 10 being the sample size for each of the samples. 10 coin flips. So I can just say, okay, it's going to run all those same things. You can see here we have 20 in our sample. Our mean is now 4.56. So we're actually getting towards that 5. Remember that if we did infinite number of 10 coin flips, so an infinite number of samples with a sample of 10 coin flips, we said that the population value should be 5. We're already kind of getting pretty close. Sometimes that doesn't happen, but in this random case, we are. And then let's look at the standard error of the mean. So the standard error of the mean is 0.61. I'm going to ask a very simple question. So how is the standard error of the mean is now compared to with 10 samples? Should be pretty obvious. It's getting lower. So remember that the formula for this, for the standard error of the mean, I'll show it so you can kind of visualize it, is the standard deviation over the number of samples, so n, the square root of that. So what that means is the more samples we have, the smaller this number of standard error will be. So this gets larger, this will get smaller. And so it relates to what I said earlier, is that the more pieces of information we have, the better estimates we can make about the population. That's simply what that's saying. So mathematically, that should sort of make sense too. We're seeing it already, but mathematically that should make sense. Is the more information we have, 20 samples now versus 10, we should have a better estimate of the mean, and we do. Let's look at the shape of the distribution. Let's go down here. Looks a little bit weird. I would not call this normal. It kind of looks skewed, perhaps. It's a little bit bumpy here. I'll call it bumpy because there's some bumps up here, and then looks like there's a skew, a positive skew here. So it's definitely not normal. So I'm going to use the scientific phrase of bumpy with a positive skew. And again, I think a big thing I want to put here is it is not normal. Okay, let's keep on doing this, but we'll accelerate a little bit more. Let's add 20 more people. So if I was in class, I would ask 20 more people to give me their data. Their data would be the number of heads they got out of 10 coin flips. And so we're going to have 40 samples. So we had 20 people so far. We're going to add 20 more people. Again, these were randomly generated by a computer to simulate the coin flips. Let's add these to our sampling distribution, I should say. So I'll add this. I'm going to double check it before I run it. And we can see here we're at 40. And you can see here also when we run it. So we'll run the same thing. We'll run the frequency to get all the information we need. So here it says we have an n of 40. So it means we have 40 samples of 10 coin flips. What's our mean now? Our mean is 4.75. I'm going to write that down. This is actually working out pretty good. I'll actually round it up. Actually, it's 7.5. We should probably keep it that way. I did some rounding earlier. That's okay. So 4.75. So we're getting closer to 5 now. Sometimes it looks a little bit, this is kind of overly perfect, but this is random. I guarantee you that this was random numbers. I didn't cook the books here. Sometimes it jumps a little bit up and down, and then eventually gets towards 5, but we're getting towards 5 right away. What's our standard error of the mean? Standard error of the mean is right down here. It's 0.44. So we're getting smaller. You can see it's going pretty fast. We're already almost half of our original standard error, and we just went from 10 to 40. And we're already roughly half of the standard error that we started with. So again, what does that mean? It means that we're able to make better estimates. We can see that mathematically. Mathematically, as our number of samples increases, this will decrease just naturally. But think about it conceptually. Conceptually, we're getting more information, we're getting more samples, and because we have more information, we can make better estimates. Let's go ahead and look at the distribution. Let's see here. It's a little less bumpy, but there's still kind of a bump over here, and it's a little bit, there still is a skew here, but the skew is a little bit less. I still would not call this normal, but it's getting less bumpy and less skewed. Hope you can see that. You can pause it if you want to look at it a little bit more. I'm going to say a little, scientifically speaking, a little less bumpy. And it's a little less skewed. But I would say definitely it is still not normal yet. Let's continue this, because I want to sort of demonstrate this. Let's add 20 more people. So let's go from 40 people, 40 samples, to 60 samples. And let's go ahead and do that. So here's 20 more. I'll simply cut and paste it. I'll get rid of these analyses. So now we have 60 people. We have 60 samples of 10 coin flips. That's our sampling distribution. We have 60 samples of 10 coin flips. Let's go ahead and run this. Here's our numbers. So let's look at the mean first. The mean is 4.82. Look at that. We're really approaching 5, which is the population value, in just 60 samples. Again, sometimes when I do this, it kind of jumps up and down here a little bit, but right around this time, it starts a definite direction towards the population value. Let's look at the sampling error of the mean. It's the thing on the bottom here. So it looks like it's 0.38. So we're still going down. Maybe it's going down a little bit less, but we're reaching a limit. There's a certain limit we can't get below, essentially. So we're still going down. As we add more pieces of information, we're able to make better estimates. Let's look at the distribution shape. It's looking more normal to me. It's certainly not normal, not a perfect normal curve, but it's looking more normal. Let's call it some bumps. There's some bumps here, but it's a pretty low sample size. So a difference between 7 and 3 looks pretty large with the sample size. So there's some bumps, but going towards normal. Some bumps. And we'll just say going towards normal. Oops, I keep on trying to say that. Sorry about that. Let's add another 20. So we have a sample, number of samples would be 80. So we add 20 more people. So 20 more people, flip the coin 10 times. What I would do in class is I would just do several rounds. So we would do 2 or 3 rounds of coin flips with everybody adding to the numbers here. And so we're going to have now 80 samples. Let me add this to our numbers. We'll confirm this. We have 80 samples. You can see here we're still getting extreme scores. We still have 10 heads and 1 head, so it's not like the samples themselves are all going to be 5. They're not. There's still a wide range of numbers there. But that doesn't matter because the more samples we have, things kind of even out. So let me run this. So again, we have 80 samples. What's the mean now? So it says 4.86. 4.86. Again, you might say, well, it's not a big jump, but well, there's a limit here. We're getting pretty close to 5. Maybe the steepness of the change is not as much as before, but we're still going towards 5, and we're going that direction. And there's not much to change. We only have 0.14 away from 5 at the moment. So we really can't change that much because there's not much distance now between the population value of 5 and our estimate of that, our mean of the sampling distribution. So mean of the sampling distribution, mean number of heads out of 10 coin flips is getting very close to 5 already. The standard error is 0.33. 0.33. So again, it might not be a major change, but we have some limits where you can't have a 0 for standard error. So 0.33, so it's going down. So the error in our estimates of the mean in this case, it's going down, which means we're making more precise estimate of the mean. And you can kind of even see here, we can see that with the mean number, and then the standard error is sort of telling us also that we're making pretty good estimates. Let's look at the shape of the distribution. Okay, this looks, it's a little bit less bumpy. You can see here it's getting a bit tighter. There's a bit more towards the middle than before. Remember in our early distributions it was kind of flat and there was a lot of things away from the mean. That's starting to change now. So I'm going to call this, it's definitely not super normal yet, but I'm going to call it tighter. We're starting to get a distribution that's tighter around the mean, which we're kind of approaching a normal distribution here as we get tighter around the mean. Let's do this last one. Let's add 20 more samples, so 20 more people flipping the coin 10 times, counting the number of heads. So now our sampling distribution has 100 samples in it. Again, those are randomly generated by a computer just to sort of simulate the coin flips that we would normally do in class. So, yep, we have 100 samples now. Let's go ahead and run this. So here it says n is 100, so we have 100. Our mean is, look at that. I hadn't looked at this before. 4.98. That is pretty amazing, but mathematically I'm not super surprised by that. 4.98. We are on the doorstep of 5.00. Just with 100 samples. And again, that 5 we would see with an infinite number, millions and millions of coin flips, it would be 5.00. But even with just 100 random samples, we're very close to that. What is our standard error? Our standard error is 0.29. So again, it's going down. It's gone down every step of the way. This whole column, the more samples we have, the more pieces of information that we have, the better our estimates are. I'll probably use this metaphor later in class too, as we go along in the semester. But one way to remember this too, if that just sort of doesn't click, is if I ask you, who would make a good partner? Making that estimate. So we often go on dates and we make some sort of informal estimate about how good of a partner they would be. Is this going to be a long-term relationship? What kind of estimates would you make about what sort of long-term partner they would be if you just had one date with the person? I hope a lot of you are saying not very good. How about 3 dates? It gets better, but still, I'd be a little bit worried about that. Maybe we won't call them dates anymore because maybe after 3 or 4 dates, you don't call them dates. But let's say you're with the person 100 times. You're hanging out with them 100 times. Well, the estimate gets better, right? You hang out with them 500 times, the estimate gets better. So just like dating, the more dates you have, the more time you spend with a person, the better your estimates are about whether they're a good long-term partner. Same thing for statistics. More information, better estimates. Just a side note, this is why you shouldn't fall in love on the first date. So if you didn't have a human emotional reason not to fall in love on the first date, you now have a statistical reason for not falling in love on the first date, or on the third date, or on the 10th date even. And so let's look at the distribution. So that's our last part here. Let's look at it. I don't know if I'd call this normal, but to me it feels like it's getting a little bit more tighter around the mean here. So what we saw at 80, I think, is still happening here. It's a little bit more tighter. We still have some bumps here. What would happen is if we kept on doing it, these bumps would kind of smooth out and would be more normal. Let me just sort of say that again. It's actually kind of like this. It's like we saw here. So the big point here is as we have more samples, we're getting very close at estimating the population mean. It's approaching the population mean. Our estimates are better. Our standard error is going down, which means our estimates are better, more information, better estimates. And the shape of the distribution is starting to look like a normal distribution. I wouldn't normally do this. I would just take another 100 randomly generated, but these are randomly generated numbers anyway. So what if we just kind of did this? And I don't know why it's not going all the way up to 1. There we go. I'm just literally going to copy all these and see what the distribution looks like. Because these are all random, actually, so you could actually do this. I would take 100 new ones normally, but let's just do this really quickly. Curious what the shape of the distribution would look like. It's actually still a little bit bumpy. So it probably will take a little bit more. Actually, what I'm doing is I'm replicating the distribution. So I should have ignored that. I shouldn't have done that. But as more random samples are collected, those bumps would go lower. It would start looking like a normal curve. So I want you to remember those 3 things, because that's what we observed. We observed that our mean approaches the population mean. If we took an infinite number of 10 coin flips, those samples, an infinite number of 10 coin flips, our mean would be 5. It'd be 50-50, 50% chance. So it'd be at 5. We're very close to that. As our sample size increases, we have more samples we're looking at in our sampling distribution. Our standard of error of the mean goes down. Our estimates are better. More information, better estimates. And the distribution went sort of from flat to bumpy to a little less bumpy to being more normal. So remember those 3 things that we have observed in this demonstration. So this just summarizes what we just saw. And by the way, I did this in class, and this worked out also in class, many times in class. So again, don't think that those random numbers that I generated are somehow special. This has always worked out in class because there's a mathematical reason why. So again, the more samples, the sampling distribution mean gets closer to the true value. So we talked about the population value. So more samples, the closer we got to 5. 5 is the true value. 5 is the population value. The more samples, the closer it gets to a normal distribution. So we saw that. And the last thing is the more samples, the standard error goes down. We have a tighter distribution around the mean. That's what was happening also. So, whoops, sorry about that. So our standard error is going down. We're having better estimates. And it's getting tighter around the mean, because remember, in a normal distribution, a lot of the scores are very close to the mean. More than 2/3 of the score are within 1 standard deviation of the mean. So it gets very tight in the middle of a normal distribution, and we're seeing that. And when we have that happening, our standard error goes down. Our standard deviation is going down, right? So the distance from the mean is getting smaller because we're starting to have a normal distribution. Remember these three things well. And these are the three things that we learned by doing that demonstration. So just to reiterate, we did a sampling distribution. We took samples of the same size. So the samples were all 10 coin flips. And it's from population. The population is all coin flips that can never happen. So we sampled coin flips. We calculated a statistic for each of the samples. So we had the number of heads, and we had a sampling distribution of that. We could do a sampling distribution of the means also. So if I did the narcissism thing, I took different samples. Let's say of 100 people, I got means of narcissism. I could put that into the SPSS. So it would be the mean for the samples, and then I could have a sampling distribution for the sampling means. Here we basically had a sampling distribution for the number of heads out of 10 coin flips. Doesn't really matter what the statistic is. You could do any statistic, but oftentimes we use sample means. And I was using the coin flip to sort of approximate that. And then we calculate overall statistics for the sampling distribution. So that's what we did. In SPSS, we took all of the samples. So we went from 10 samples to 20 samples to 40 to 60 to 80 to 100. And for that sampling distribution, with those samples, we calculated the mean, we calculated the standard error, and we did a plot of the histogram, the frequency histogram, for that statistic, number of heads out of 10. That's what a sampling distribution is. So we just did one. Hopefully that makes a lot of sense since we demonstrated that. This just shows what we did. So if we think about the mean instead, we can actually think about this. So the population value would be 5. And then we had some samples had 10, some samples had 1, some had 3, some had 4, some had 5. So each of these things are samples. And as we demonstrated, we can plot this on a frequency histogram. And this is actually a good example of what it would look like when we have more samples. So frequency is the number of samples that have this. So whatever the sample mean is, here in this case we had over 100 samples that had that. It's the same thing that we did with our distribution with our scores here. I took it off the output, but I'll put it back on. Again, this is just a frequency histogram. These are the number of samples that had 5 10 coin flips, or 5 heads, I'm sorry, out of 10. These are the number of samples that had that. So these are the frequencies, number of samples. So again, when we do more of these, we have more samples. In our sampling distribution, we'll approach normality. We showed that in our demonstration, but we didn't have enough samples. We left with 100. But if we did more than 100, it would start looking like this. This is probably around 1,000 samples, I'm guessing. It starts looking a lot more normal. So just in summary, you know these 3 things about the sampling distributions. As we have more samples, the mean of the sampling distribution approaches the mean of the population. Officially, we can say the sampling distribution of the sample means. So you find each sample. From each sample, you find their mean and you plot it there. So you're plotting the means for each sample. If you take the mean of that, if you take the mean of all those sample means and you increase the number of samples you have, it's going to approach the population mean. Just like, I know you might be getting sick of this, but I want to show you, this is what we did. This is what we're saying here. We increased the number of samples, we approached 5. We approached the population value. That's what this is saying, just a little bit more formally. The standard deviation of the sampling distribution of the sampling means, the standard error of the mean, is decreasing. The standard error of the mean is decreasing. And this gets a bit more complex, but I just want you to think about what we saw in our demonstration, that the standard error is going down. By the way, the standard deviation is going down too, but I just want you to think about it as an estimate. The estimates are getting better. And then we saw that the shape of the sampling distribution approaches normality. And so we actually are going to see something on a video in a bit. And in that video, it will actually demonstrate that this is true even if you have a non-normal distribution, a non-normal population. I will have the video explain that a little bit more. It will demonstrate that. But again, those are the three things. And again, I want you to not get caught up in a bunch of words. I want you to think about the concepts. More samples, we get towards the population value. So the mean of the sampling distribution approaches the population mean of 5 in this case. Our standard error decreases, our standard deviation decreases also. And the basic thing I want you to remember about that is that we're making better estimates with more information. And then a huge thing is that the more samples we have, the closer we get to a normal distribution. What are those things that we just did? It's actually called the central limit theorem. So what I just showed you, it was a little bit more technical in its wording, but really the central limit theorem says what we just said. These three things. Our mean of for the sampling distribution approaches the population value, the population mean of 5 in this case. Our estimates get better. We see that because our standard deviation decreases, the standard error decreases. And the shape of our distribution approaches normality when we have more samples. The three things that we did in our demonstration are essentially and conceptually what is in the central limit theorem. So if you're ever asked about the central limit theorem, think about those coin flips. Why is the central limit theorem so important? Why are we taking this time to do these things? Because this allows us to do inferential statistics. Why? Mainly because of, well, there's several things here. Let's just take all of them. We know that we can make better estimates with more information. And so that's part of it, but the big part of it is this normality. So even if you take just one sample, and let's say that sample is even non-normal, we know we can make some sort of prediction off that sample because we know if we take lots of different samples of the same sample size and we look at the sampling distribution, that sampling distribution would be normal. If we have sampling distributions that are normal, it will allow us to make precise estimates, precise probability estimates, and therefore we can use information from our samples to make inferences to populations because of this very thing, because of the central limit theorem. So we don't take sampling distributions. So when we do research, we don't take a bunch of samples of the same size. We take a sample and we make inferences from that one sample to the population, and we can do that because of the central limit theorem. Because underneath the central limit theorem, we know if that we took many, many samples of that same size, we would fall under the normal curve, and we can make very specific probability statements. Probability statements about how much our sample's data applies to the population. And that is the core of inferential statistics, making those probability statements. And those inferences are specifically about whether there's an effect or not. So in our sample, for example, if we found a difference between our treatment group, a group that we did something to, versus a control group which we didn't do anything to, is that difference large enough to say there's an effect there? And whether that difference applies beyond the sample, applies to the population. So I think one of the things that I've been talking about in this class is, for example, if I had a memory strategy that I think helps people remember things, I could do an experiment on that. I could take a sample of people, and half my sample, I will give them my memory technique. I'll say, read this thing, use this memory technique, probably developing a story about the thing that they're reading. Make it a personal story. That will probably help them remember. Then I'll have a control group, and I'll just say to the control group, just read this and you'll have to remember it. I won't give them a strategy. And so that difference between the treatment group, where I gave them a new memory strategy, and the control group, which I didn't give them any memory strategy, if they differ, if my group that I told to do the special memory strategy did better on the memory test, that would show that there was an effect of my manipulation, of my independent variable. But we don't know whether that is something we can say is true for the population without the central limit theorem, without the normal curve, without these set probabilities. So hopefully you're getting a little bit of a grasp of this, is that the central limit theorem helps us do research because we don't have to worry about our sample being perfect, because we know if we took samples of the same size from the same population and ran the same research, we would eventually fall under the normal curve. Once we have the normal curve, that has stable probabilities, stable properties. So remember our z-tables? So every standard normal curve has those percentage of people underneath the curve. And we then know the probabilities in terms of, remember I talked about likely and unlikely events at the beginning of this lecture? So if my mean is higher for my memory strategy group than the control group, but the mean, let's say, is only 1.2 standard deviations above the control group. Well, that's not very far, right? That's actually a pretty likely probable outcome. Just randomly, there'll be a lot of scores, a lot of memory scores within that range. So it's not very good evidence. But let's say that I have a 3 standard deviation difference between my memory strategy and the control group. That's a huge difference. That's very unlikely. If it's very unlikely, we can say that there's evidence that that memory strategy helped people remember things better. So the stable properties under normal curve, we can actually start talking about what things are likely and what things are unlikely. If they're unlikely in terms of random chance, then maybe it's the thing that we did. Maybe it's the manipulation we did. Maybe it's the treatment. So inferential statistics deals with those things. It uses the normal curves, its stable properties, to talk about what's likely and what's unlikely. And again, this we can do because of the central limit theorem. Even when our sample is not normal, we don't have to worry about it too much, because under the central limit theorem, we know that if we take a sampling distribution of the same size with many different samples, we go to the normal curve. So again, this underlies all inferential statistics. And again, I don't want to get too esoteric here. If you ever get lost, just remember what we did here. This is the essence of what we did here, and this is the essence of inferential statistics. We approach normality. And so we're going to be making this bridge. So we've been making a bridge from z-scores to sampling distributions to inferential statistics. So now we have the theory and the reasoning behind inferential statistics. Z-scores, remember z-scores, we can't tell whether a score is really that different from the mean unless we compare it to the standard deviation. And then we can start looking there to see about things like percentiles and how many people are below that score. How different is that score from the mean? How far is it from the mean? Is it close? If it's close, it's a very likely score. So it really doesn't mean that much. It's not that big of a difference. But if that score is far away from the mean, in terms of z-score, standard deviations, then we can say, oh, that's very different. Then we can say something about that score being higher. And now we looked at samples. So just like with people, can we make inferences about our sample? Yes, we can. The central limit theorem says that. We can take samples, and even if they're not normal in terms of their distribution, we can use the central limit theorem to say we're going to make better estimates if we have a lot of pieces of information. And most importantly, we can use that normal curve to make those probability statements about our samples. So that normal curve stuff that we were doing with z-scores doesn't just apply to a score and a mean. It applies to the logic of samples also. The information from our samples, is it something that can be applied to, and we can say that there's an effect there that will apply for the population. So hopefully this lecture made some sense. We did both ends. We did some sort of conceptual stuff mainly at the end here. I hope you were able to understand that. If you weren't able to pick up all of that, that's okay. We'll be doing more of it. As we go along, it'll be more concrete as we have real statistics, but also just as a demonstration. So we demonstrated with our coin flip example that we approach normality. We approach normality, and therefore we can make these inferences from samples to populations. We talked about this in class already. I won't cover this again. This should be pretty easy to answer. Would we be able to better predict our population mean and standard deviation from a sample of 20, or a sample of 50, or a sample of 100? I hope you say 100. So just remember, more pieces, the better the estimates, the better the predictions. And we actually will get into that with inferential statistics. In inferential statistics, we're always going to use the normal curve, but those normal curves will be, in essence, adjusted for by the sample size. So the larger our sample sizes, the better our predictions, and the more confidence we can usually have in terms of making our inferences from the sample to the population. We'll get into this in more detail later in the course. But just remember that. That would be a great thing to remember. More pieces of information, better estimates, better predictions. We have more certainty in making inferences from that sample to the population. This figure says exactly what we're just saying, except it talks about the prediction in terms of standard error. So this, as it gets lower, as our errors get lower, our predictions are better. And we can see here that it goes down pretty quickly. And we actually saw this So if you remember, our standard error went down really fast from about 10 to 40. And then it kind of flattened out a little bit right here because there's, you can't get to be perfect. There's always going to be some errors, but it was very quick, 10 through 40, and then it kind of slowed down over 60. Let's see if it matches. I haven't looked at this table. I didn't look at this table in doing this. But look at that. It goes down really quick until about 40, and then it kind of levels off a bit. So we saw that also. But basically what this graph says is the more samples, the more pieces, the larger your sample size, the better your estimate, the better your predictions. The more dates you go on, the better prediction you have about your partner. And what's really interesting is that these samples don't have to be huge. Right around 50, we get to almost no difference between 50 and 100. So in terms of psychological or any research, once we have samples around 50, we're getting fairly good. We're getting fairly good estimates. And oftentimes you'll hear 20. Sometimes people will say 20. You can kind of see why. So 20 is kind of the biggest leap. So sometimes people say, well, you should have a sample of 20, but the reality is if you want a really good estimates, 50 is about that. Again, the big point is you don't need a ton. I don't need a sample of 10,000 people. I don't need a sample of 100,000 people. Once I reach to about 20 to 50, I'm already getting pretty good estimates. And 50 is almost as good as 100. And why is that? Well, part of the reason why this is again, the central limit theorem. The central limit theorem, as we add on these things, the standard error drops really quickly. So just to sort of get to the end of this lecture, so in inferential statistics, as we saw here, the number of pieces of information that we have matters. If we have fewer pieces of information, we're not sure about our inferences. If we have more pieces of information, we can be more sure about our inferences in terms of saying what we saw in our sample applies to the population. So we have a notation for this in statistics. We'll talk about this more later, but basically it's called degrees of freedom. So degrees of freedom, there's different ways of calculating. Essentially what it is, it's an estimate of the pieces of information, number of pieces of information that we're using in our stat. So we'll talk more about this later, but that concept, degrees of freedom, it's simply just telling us how many pieces of information are you making your estimate from, your prediction from, your inference from. How many dates did you go out with this person before you made a conclusion about whether they're a partner that you want to be with or not? That's what degrees of freedom stands for. And we'll get into this in more detail as we get into inferential statistics after this lecture. So degrees of freedom, just a little piece of information in general. It's n minus 1. What's n? Is the number of pieces of data you have. Why is it n minus 1? Well, it's a little complicated, but basically it says degrees of freedom. So the best way to think about this is if you have, let's say we have 30 people in class. I'm going to illustrate it this way before we get into the conceptual too much. Let's say I have 30 people in class. So I give you a quiz, let's say. And so everybody has a quiz score. And I know what the average is. I know what the average of the class is. So what happens is if I know 29 people's score, I will know the 30th. So that's why it's n minus 1. So if I have 30 people in class, n, degrees of freedom would be 29, because 29 people, I'm not sure what their score is. But one person, I would know what their score is, because if I know 29, I would know the last person. So that's why it's n minus 1. It might seem a little bit arbitrary, but that's essentially what it means. But I want you to remember conceptually what it means. Conceptually, it means the number of pieces of information that we're making our estimates, we're making our inferences based on. And the thing is, the higher the degrees of freedom, the more pieces of information we're making our estimates on, we're making our inferences from. That's what that means. So higher, larger degrees of freedom, more pieces of information, the better our estimates, the more confidence we can have in our inferences from the sample to the population. Smaller degrees of freedom, fewer pieces of information to make estimates on. We are then a little bit more uncertain. We have to be more tentative about our inferences from the samples data to making conclusions about the population. And what we'll see is we'll use this number. When we do inferential statistics, we're actually going to be using this number to make our inferences. And that's basically the principle. More pieces, we know we have better predictions of something. The more dates, we make a better prediction about the person, whether they should be our partner or not. And that's going to make our inferences, our conclusions, stronger from a probability standpoint. Smaller degrees of freedom, we have to be a little bit more tentative, and so our statistics are going to account for that. When we do inferential statistics, it will account for the pieces of information that we have. And it will make us be a little bit more careful if we have fewer pieces of information, lower degrees of freedom. This will become clear as we have real examples as we go along in our class. So just to review, sampling distributions, we take multiple samples. They're all the same sample size. We took multiple samples of 10 coin flips. We combine information from those samples, and we can make a sampling distribution. So we had a sampling distribution of the number of coin flips out of 10. And then remember the central limit theorem, but I want you to remember it the way we did it, because I think you'll remember that better than the specific language of the central limit theorem. Remember, the central limit theorem is just saying three things. As our number of samples increase, and so as the number of pieces of information that we have increase, our mean from the sampling distribution approaches the population mean. So if we looked at the mean number of heads out of 10 coin flips, that really approached 5 very quickly in our sampling distribution. We were at 100 samples and we were almost there. The sampling error of the mean decreases, so we're making better estimates. We're getting closer to population values. So one big thing across these two things is we're making better estimates. From our sampling distribution, we're making pretty good estimates about the population value of things as we increase the number of samples, as we increase the number of pieces of information that we have. And the huge thing is that we approach normality. So we saw as the number of samples increases, we approach normality. But you're going to watch a video, and in that video, you'll see that also when our sample sizes are increased, that also increases the normality. So let's say instead of having 10 coin flips, let's say we had 100 coin flips. So we had each person do 100 coin flips. So we had a sampling distribution where each sample was 100 coin flips. I think you could find out pretty easily in your head, you can sort of think about this, is that if we did that, we would approach normality a lot quicker. We have more pieces of information. So we approach normality quicker if we have more samples, and we approach normality if those samples are larger in size. Again, the basic principle here is the more information we have, the more it will approach normality in a sampling distribution. So I want you to do some things now. There's no homework and there's no lab for this lecture. So I want you to watch this Khan Academy video. It goes over the central limit theorem. It goes over it not necessarily conceptually, although there's some conceptual stuff. It will actually give a demonstration. So we did a small demonstration here now in this lecture, but do watch this. It's going to actually give you a larger demonstration of the central limit theorem. It doesn't take that long. It's 11 minutes. The link is in the PowerPoint here on Canvas, so look at that. And if you want to sort of review it, so in that Khan Academy video, the instructor is using this number generator. So if you want to play with it, this is the link for that number generator. And again, it's in the PowerPoint. And this is just a summary of the central limit theorem. So there's three properties again. The mean of the sampling distribution of the means approaches the population mean. What does that mean? Well, it means for us, the mean number of heads in our sampling distribution, it approached 5, the population value, as our number of samples increased. And one last time I'll show this. The standard error starts approaching the standard deviation of the sampling distribution of the means. That's very much a mouthful. What I want you to remember is we make better estimates. Our standard error gets smaller. We make better estimates. So I want you to remember that. So if you don't put down this formal language, I'm okay with that. I want you to remember we make better estimates as we have more information, as we have more pieces of information. And then the last thing is the distribution shape approaches a normal distribution. This one. So again, we have sort of the formal ways of stating the central limit theorem here in the PowerPoint, also in your textbook. But what I really want you to think of, you think central limit theorem, think about the three things that we observed in our demonstration. And we talked about this already a bit. So again, the central limit theorem allows us to do research. It allows us to do research with just one sample. The central limit theorem basically is telling us is that our samples in a group of other samples in a sampling distribution, and while your sample may not be necessarily perfectly normal, if we think about probabilities in terms of all the different samples in the sampling distribution, we can use the normal curve. So the central limit theorem allows us to do research because now we can take one sample and make some inference from that sample to the population. But again, we have to do it with probability statements. And again, we have some caveats here. So the larger our sample, the more certain we are. The smaller our sample, the more unsure we are. So that gets adjusted in terms of our probability statements. How much we saw the stuff in our sample will actually apply to the population. As we go on with inferential statistics, you're going to be seeing this thing p less than 0.05. What that just is saying is that it means that the probability of something happening is less than 5% due to chance. What does that mean? So as I continue this, just sort of keep in mind that this might not click 100%, but that's okay. But remember we did our z-scores and we had the normal distribution curve, and we had the mean, and the mean is the z-score of 0. So remember the z-score is 0 here. And then we had z-scores that related to the standard deviations, and they would go out like this. And remember we talked about, we talked about that because of the nature of the normal distribution, there's a lot of scores here. So if you're getting scores around here, just by chance, you're actually not that far from the mean. It's very likely you'll have scores in the middle here. It's very likely. These are very likely things here. If you get a score way over here, it's not likely. And what does that p is less than 0.05? It means that when we look at the normal curve, there's only a 5% chance that randomly you would have a score way out here. It's not very likely. So when we do research, let's say we're doing research on, there's a control group here. If we have a treatment group, in my treatment group, let's say the memory thing I talked about earlier, if my treatment group mean is like that, it still is above, and you can say, well, oh yeah, there is something there, but no, we can't. In terms of inferences, it's pretty likely to have a mean in this area. It's very likely due to chance. So what we say then is we say that there's not really evidence there for an effect. If the mean of my treatment group, so the ones that I gave a memory strategy to, if their mean is way over here, it's very unlikely, and we know from the normal curve that in fact it's less than 5% chance likely. Then we can start saying there's probably something there. Probably the memory strategy that I gave to this group helped them remember things better. And we can say that because there's only a 5% chance that I would have such high scores just randomly. So it's very unlikely. It's an unlikely event. Not likely. And so we can kind of flip this and say that there's sort of a, I'm 95% confident, if you will. I'm 95% sure that my memory strategy had some impact on helping people remember what they read. That's what inferential statistics is, and that's what the p is less than 0.05 says. So all of this should be coming together now. So the z-scores, when we looked at an individual score versus a mean, we could see how far it was away from the mean. And now we're looking at samples. So with the sampling distributions, it's saying with one sample, I can look at these things and I can make inferences from the sample to the population without having any other samples. Why? Because the mathematical principles of the central limit theorem allows me to make these probability statements. Allows me to use the normal curve to say something about the population based on just one sample. So this is a little bit repetitive, so I apologize for this, but I just kind of want to repeat these things. So the central limit theorem allows us to do research. Why? The central limit theorem allows us to use the normal curve. That normal curve, sometimes we call it standard normal distribution, it has very predictable qualities, especially those percentages under the curve. This thing I just showed you, these percentages of what's likely and not likely in terms of exact 5% chance that you would be this far away from the mean, that's stable across all standard normal distributions. Because of that, I can do research and I can say specifically what those probabilities are. It allows me to make very precise statements about inferring something from my sample to the population. And the central limit theorem essentially says, well, you know, these are great things. The normal curve is a great thing. We can make those very specific probability statements. Those very specific statements allows us to do research and say, how confident are we what we saw in our sample will be seen in the population? And the central limit theorem says, don't worry. You can do this with one sample because we know that your sample is part of a larger distribution of samples. And when we look at that larger distribution of samples, if we have a bunch of samples, it's going to approach the normal curve. So it's okay to start using that normal curve with just one sample. And this is really important because of the central limit theorem, nobody can really say, well, your sample's weird. You can't do anything from it. Because inferential statistics takes into account your sample size, your degrees of freedom, how much pieces of information you have that you're making estimates from. So it says that we can use the normal curve even with just one sample. So without the central limit theorem, we would not be able to do research because people could say your sample's weird. Anytime you took a sample, somebody could say your sample's weird, your sample's weird. With the central limit theorem, they can't say that. Because with the central limit theorem and with taking into account the number of pieces of information you have, the largeness or the smallness of your sample, we take into account all of those things and we can still use the normal distribution to make probability statements from the sample to our population. So I don't know if I'm going to repeat this. You can kind of sort of pause this. But again, this is a way that I can say in this case, I'm 95% sure that my thing worked. With just one sample with the central limit theorem, central limit theorem says even though I have just one sample and even though my sample might not be perfectly normal, I can still use the normal curve. And then we also take into account the number of pieces of information. So when we do inferential statistics, you'll see that we will take into account the number of pieces of information. We'll say, oh yeah, we're pretty confident with more pieces of information, a larger sample size. If we have a smaller sample size, we have to say, wait a minute, we have to be more careful. So when we look at all of this stuff, it allows us to do research with just one sample. Without these things, we could not do research. We could not do research. People would always say our sample's weird, and therefore you can't say anything about the population based on your weird sample. With the central limit theorem and taking into account the number of pieces of information we have, we say, no, that's not true. Doesn't matter if my sample's quote-unquote weird or different or not normal. Doesn't matter. Central limit theorem allows me to use the normal curves as long as I take into account how big my sample is. And this is really important. These probability statements, they're stable. And they're very accurate. I can very, very precisely say what's the probability that my sample's data applies to the population because of the normal curve. We don't have to sample the whole population. We can take samples, and our samples don't have to be large again. Remember that graph about the standard error? We get fairly good with 20. But we get really, really good with about 50 to 100. We don't need large samples also. So we can take one sample, and the sample doesn't have to be huge. It can be around 20 to 50. 50 to 100 is better. But even with the 50 to 100 people, I can infer my findings to a much larger population. This allows us to do quantitative research. So that's it for this lecture. I know that some of the points were repetitive, but I really wanted to kind of reinforce them because they're very important because they underlie all of inferential statistics. So next time we'll talk about research a little bit more specifically. We'll start looking at research methods, and we'll also start getting into hypothesis testing. So hypothesis testing is where we get more formally and more specifically into inferential statistics. So inferential statistics are about testing hypotheses. And by testing hypotheses, that allows us to make inferences from our sample to our population. So hopefully this lecture was good. I know that there was a lot of repetition in it, but I wanted to repeat the main points. And if you have any questions, please come to our Zoom sessions and ask. Otherwise, I will talk to you in the next lecture.